Hello everyone, welcome to the second part of this week's lecture. Now we'll turn our attention to deep learning. So we'll first explain what is a simple feed-forward network, and then we'll look at what the computational graph looks like for deep learning, and then we'll quickly go over different types of neural networks like convolutional networks, recurrent neural networks, and just look at the architecture of each one of these networks. And finally, we'll talk about some applications of the different networks. So the feed-forward network essentially is a set of layers. Each layer is made of what we call neurons. And the data can only flow in one direction from the input all the way to the output. So that's what we call directed cyclic graph with designated input and output for each node. So there are no loops in the network. A recurrent neural network, however, will have loops, as we will see later on. It will allow loops to take into consideration time. So a network within a node within a network is called a unit. And essentially what it does is it calculates a weighted sum of all its inputs from the previous nodes from the previous layer, and then applies some nonlinear function to this weighted sum to produce its own output. And then its own output becomes the input to the nodes in the following layer and so on. So essentially the training process is about finding the weights here, wi sub j, from essentially input of unit j, and wi sub j is the weight of the link from unit I to unit j, and finding these optimum weights to minimize a given loss function. So it's up to us to select the loss function we want to minimize, but essentially the entire process boils down to finding these optimum weights to minimize the loss function. Now, there are different activation functions. So the function g sub j here is called an activation function. The most famous ones is first the logistic or sigmoid function. This one is very popular, as we saw before, because it doesn't have a sharp edge, like we said. It smoothes the transition from 0 to 1. There is a ReLU function, which is also very popular. This one takes the max between 0 and the output from the node x. So ReLU of x is max of 0 and x. And then there's also the hyperbolic tan function, which is popular as well. So you can see the formula there, tan h of x, e to the 2x minus 1 over e to the 2x plus 1. So x in each of these cases is essentially this weighted summation over I of all the inputs into the node j. So typically we select one activation function for the entire network, except for the output layer. It will have its own activation function. But for all the hidden layers and the input layer, typically we just pick one type of activation function. And the most popular one currently is the ReLU function. It leads to the faster conversions. So this is an example of a network. So x1 and x2 are the input layer. So we have two inputs here, x1 and x2. And then we have one hidden layer, which has nodes 3 and 4. And then one output layer, which is node 5, and its output is y hat, which is the predicted value, whatever its regression or classification. So as you can see, node 3 has two inputs. One of them is from node 1. So this is a weight we're going to give to this link is w1, 3. And then it has another input from node 2, which weighted by w2, 3. And then we calculate the sum of the weights times x1 and x2, and then apply our activation function and generate the output, which will go into node 5. Okay, so the output from node 3 is going to be weighted with the factor W3, 5, and will go into node 5, and same for node 4. So our algorithm essentially for training this network is going to be to find the optimum weights, all these weights, 1, 3, 1, 4, and so on, such that the difference for any training example x1, x2, for which we know the correct answer y, to minimize the difference between y hat, which is the output from our network, with the true answer y. So that's true whether it's classification or regression. We're always trying to match the true output that we have in our training data. Remember, this is supervised learning. So for each example, x1, x2, we already know the true output. Now you notice that in addition to W1, 3 and W2, 3, we also added in the for node 3 here, we added another term, W0, 3. So this is called the bias term. So this one is not multiplied by anything, it's just a bias term that's added. So all these nodes, 3, 4, and 5, will have their own bias term. The input to the bias term is just a 1, so it's 1 times the bias essentially. So the only thing we need to weight here is, again, a simple weight W0, 3 or W0, 4 if the bias for node 4 and so on. So as I said, the goal is to minimize the loss function. So the prediction from our network is y hat, and the loss function in that case, if we use an L2 loss function, so we're doing a regression in that case, so it's going to be the sum over all the training example of the square difference between y, which is the true output, and y hat, which is our prediction, squared. Okay, now if you remember from last lecture, we said we're going to use gradient descent to find the optimum weights. So gradient descent would require to find the derivative of that loss function we're trying to minimize with respect to all the design variable in that case, which are all these weights, okay, including the bias, of course. So we need the partial derivative of the loss function with respect to all of these variables, and then we're going to put, once we found this partial derivative, that's going to give us the gradient, and then we can take a learning step, if you remember from last week, in the direction opposite to that gradient in order to reduce the loss function in the next iteration, and so on, and we keep iterating until we converge or the loss function doesn't decrease anymore. So if you look at this, it would appear that we can only calculate the derivative once we have y hat, because the loss function requires y hat, because the loss function is y hat, y minus y hat squared. So essentially, in order to find the derivative, we have to use what's called back propagation. So once we're able to find y hat, then we back propagate this y hat through the network, and at each node finds the derivative of the loss function relative to the weights of that node. So as we back propagate, we're going to first find partial L, partial W05, and then partial L, partial W35, and so on, all the way until we reach the input. So this is the back propagation step in learning. Now, our inputs, obviously, x1, x2, and so on, has to be numeric values. So in case of a binary variables, for example, male, female, or anything like that, that's easy because it's just 0 and 1. If we have a numeric attribute, like let's say the price of a variable, so something that's numeric, continuous variable, so we're just going to use it as is. And then if we have a categorical attribute, like for example, if you remember from the restaurant example, we had different types of restaurant, Chinese, Mexican, and so on, we can use what's called one-hot encoding to translate this categorical data, which is English, into numeric data, so vectors of ones and zeros. So for example, if we say Mexican food is 1000, and then Italian food 0100, and so on. So we're going to be able to essentially encode this categorical data so it's in a format that allows us to calculate derivatives and loss functions. Now, once we reach the output layer, we will determine the activation function of the output layer depending on what we're trying to do. If we're just interested in getting a probability that a given example belongs to a given class, then in that case we can just output y hat as a probability. However, if we want to get an actual class, then we can take the negative log likelihood, the loss function in that case, and just get a class. So typically the output layer depends on the task at hand. Are we doing regression or are we doing classification? Now, the key here is the hidden layers. So everything between the input layer and the output layer is called the hidden layer. And essentially each layer, what it does is it takes its input and then produces a new representation of that input as its output. And in the process of forming all of these internal transformations using the weights, the deep network finds meaningful intermediate representations of the data. So that's how neural networks converge to a solution, is by continuously transforming the data from one space to the next, and then through each transformation we learn something about the data. So the hidden layers of the network play a key role in that, and the number of hidden layers to use, and then how wide the hidden layer, how wide means how many neurons you include in each layer, is essentially what's going to determine your bias variance trade-off. So a layer that a network that's too small is not going to be able to capture the dynamics of something complicated, so you're going to have high bias in that case. The model is too simple. And then a layer that has way too many parameters will overfit the training data, and then we're not going to generalize well. So designing the network takes some trial and error in order to find the optimum number of hidden layers and how deep your network goes. So that's the number of hidden layer, and also how wide the network goes. Now, CNN are a particular type of networks that are used for computer vision application in general. And again, this type of network has a specific structure and uses, but at the end of the day, it's the same concept of input layer, hidden layers, and output layers, but it just has a hidden layers that look a certain way in order to capture features in images as they go through the network, and then based on these features from layer to layer, it's able to make a prediction as to what the photo includes, essentially, or what the picture includes. Now, I don't want to get into too much details, but let's go back to the important key here is that the gradient of the loss function is the key here to converge. For the network to learn is that you have to be able to use backpropagation. And that was the trigger for this entire deep learning science, essentially, is the discovery of this backpropagation and the ability to calculate the gradient using backpropagation through the network. So now, choosing a network architecture. Okay, so this is about to go out of time, so I'll upload this part and record a new part.